welcome everybody to today's webinar on how we can basically estimate the runtime of Simulink models. And we're going to start with the technical part in 2-3 minutes. I'll just have a very quick company introduction. Then Oliver, who will guide you through the technical part, he will give you an introduction, a bit of an outlook on what is going to be, let's say, possible in the future, what we're working on. And as you can see here, we'll look into the static code analysis and how you map from C code to Simulink blocks. And let's say also how we can use the tool in your workflows, or how we can integrate it into your continuous integration workflows. And there'll be a tool demonstration, of course. My part is the short company introduction. Let's start with when the company was founded, 2016, so 8 years now. And we're located in Karlsruhe, in the very center of the town. We're 12 people, and our focus is software products. Yeah, so we're providing software tools mostly to the automotive industry, but also aviation sector. So quite often when people have got high demands on their calculation units and some real-time requirements. Our software products are the Performance Estimator, the emmtrix Performance Estimator. This is what we're dealing with today, the tool we're dealing with today. So apart from estimating the runtimes of your code, we also look at the dependencies in your code. Both of these products are based on static code analysis. And we also go beyond analysis. We also have optimization tools. I'll talk a little bit more about that on the next slide. Together with these software packages, software tools, we also provide all the required services. So if you need some technical consulting, like for example, what kind of hardware platform should you use, then we can help you with that, for example. If you have some specific requirements, we can adapt our tools to your requirements. Already mentioned the integration in workflows, so we provide this. And of course, we also provide tool support and trainings. Yeah. Now just go to the next slide. And here, just to give you a bit of an overview of how our tools are set up. So we have got various input languages. At the top, you can see C code, TargetLink. We could also have embedded coder, AutoSAR, and C++. When you come from C++, you have to go a little bit of a detour. You go through our code conversion, emmtrix C++ to C compiler. So this is a tool that we have as well. It's a code generator. But as I mentioned earlier, our focus is on analysis tools. And I mentioned these two. So basically, you get the input, the C code, let's say, and then you get an idea, and this will be demonstrated in detail today, how this code actually performs on the platform that you are using. And as I said earlier, the analyzer will show you the dependencies in your code. Yeah, and the output then is results of this estimation, usually in the form of reports. Also, graphs are possible for the dependency analysis. The other tools that we have, they are focused on what can we do with what we've analyzed, really. So how can we optimize the code? There are two options currently, but there's more to come in the future. One is you can basically distribute the code onto various calculation units. So parallelization of the code. And as a specific type of parallelization, we have got the code vectorizer tool. Some of you will have run into this topic. For example, the emmtrix with its PPU has got a vectorization accelerator, so a unit that will make good use of vectorized code, and we can help with vectorizing code so that actually results are good. And again, this time, when we optimize, you have got as output optimized C code and equally sort of the results. All right, that's pretty much everything about the company and what we do. And now I'd like to hand over to Oliver.
Okay, thank you for the introduction. So also welcome from my side. So I will now focus on the technical side. So I will start with an introduction of the issue and then show a bit about, show a short outlook, what will be the result of the whole analysis we are doing, and then we'll bring in some more details about the technical background, what's happening here. So let's focus on the presentation. So what is the issue? Typically, a function developer or developer working directly in Simulink is modeling in the algorithm. So he has his models, his subsystems, modeling everything, but he doesn't really know too much about the actual runtime on the embedded platform. So we have an embedded platform, embedded processor, and the overall impact of a design decision. So whether to implement it, using a simple calculation, using a more complex block, is not directly visible. So the overall execution time of models is not present for the actual developer. Now, what's at stake? So what happens if you don't know that? Well, the measurements on hardware are a typical way to ensure that the timing is correct, but doing that on the hardware is really time consuming. So if you are still in the development phase, you are developing your algorithm, you need to generate code, then you need to have your hardware platform available, you need to be able to run tests, and all of that is very time consuming, very costly. And if you then see, oh, there are some issues with the timing, you have to go back. So the going back and making changes to the code during the integration phase is very costly. And it is also very difficult to find the high runners. So the actual parts of the program that run the most, take the most time. If you do it with measurement on hardware, you have to go until the hardware, make some measurements, then have your tools and analyze it, and then go back to the actual model. So what we want to do is to reduce this effort to go to the hardware and give a quick estimate before before doing any measurements. So how does our solution look like? So we focus here now on development in Simulink. So you have your model, and then you use a code generation tool like TargetLink from DSpace. Embedded coder would be a different option. You generate C code, and with the help of our tool, we analyze this generated C code so that we can generate performance report where you can directly see how much time is spent on which parts of your Simulink model. So this is static performance estimation of the source code. So we are not measuring anything on hardware or during a simulation, but only performing static performance analysis. And the analysis results are then mapped back to the model. Now, what are the benefits of doing something like this? So you have the performance estimation very early in the development process. So directly you can use it for design decisions, whether to implement it in this way or another way. Just run the performance estimation again, and you directly see the actual impact on the target platform. So you can also use it for continuous monitoring. So here the idea is that you run it automatically. So after each code change, you will see what the impact is, and you can look at the previous reports to see, was it an improvement? So is it now faster, or did you implement a lot of new functionality? Then of course it will take more time, but you can directly see the impact of everything you're doing during the whole development flow. You will also get detailed information about each of the blocks and subsystems. So it's possible to model or to understand the timing behavior of the overall model much more easily if you know where most of the time is spent. And most of the time here is typically spent in high runners. So high runners or critical parts of your model, detecting them very early is also possible with this approach. And if you're doing that, throughout the whole function or throughout the development, your code is ready for hardware tests. So your first hardware tests should not be, oh, it's not running at all, but more on the side of, okay, verifying the numbers that you get, having a bit more accurate numbers and seeing how it behaves on the actual hardware. Now, just a short outlook. How does it look like? What is the output of our tool? For instance, we generate reports like this. Here we can see there's an HTML report. You have some sections. You can select your timing. You want to have in clock cycles or in time. And this would be one example of the model. We have here the whole hierarchy. So we have an engine controller subsystem with engine controller, several modules as part of it. We can see TargetLink outports, but we can also see 37 or 38% are spent in this subsystem, 23 in this subsystem, and you can really look into it. Okay, most of the time here, for example, is spent in lookup tables. Some time is spent in these logical blocks, arithmetic blocks, so some gain. We can see here average numbers, but also maximum numbers. So here we can see engine controller average. Typically it takes around 7 microseconds, but with a maximum, you can see we have around 50 microseconds then. So here we can see a bit of the range already, what the actual time or how the actual timing may look like. Now, what are we doing here? So we are doing a static analysis of C code. And how do we do this? So we have what we need is the execution time of a block. This consists of the execution frequency of a block. So how often is a block executed in the actual program when running it? And this is actually not depending on the target platform. So this typically depends on input code, on the size of the problem. So the input data is relevant here to see how often a block is executed. And in addition to the execution frequency, we need the execution time of a block. So how long does it take to run a specific block once? And this is very dependent on the actual processor. So if you have a specific target platform, a calculation may take 10 milliseconds. On another platform, it's 5 milliseconds. And this is really dependent on what kind of hardware is available, the clock frequency, and all that, very specific on the target platform. So how can both values be estimated? So first, let's look at the execution frequency. We try to analyze it statically. So this is highly affected by the control structure of the program. So if we have loops or conditional blocks, this defines how often a block is executed. So a loop, if we can analyze it, okay, a loop is executed 20 times, then the body of the loop is executed 20 times, and everything inside or nested can be calculated from that. But it is not always possible to calculate this statically. If we look at a for loop like this, we can see here I smaller than a return value of a function. So if this is really a function, this cannot be analyzed statically, and we can always only work with default values, or we have to rely on user input when this calculation is not possible. How can we get the execution time? So the typical way we do that is to look at the C code, and we have a table for a target platform. Here we have an example, for example, a tri-core with a TC160p processor. And for each instruction in the C code, we have a cost assigned to it. Here we can see a 16-bit addition, 32-bit addition, and a number of clock cycles. If we look at the C code, then we have an addition, multiplication, assignment, comparison. So for every instruction inside of the C code, one cost. This cost here was acquired by running a software on the target platform and is an average number for multiple executions with compiler optimization 02. Now, if we look at fractions, so here it says 3.25 clock cycles for a 16-bit edition. This means on average, it will take a bit more than 3 clock cycles on this target platform. So this is depending on where the data is coming from. So on average, it will take a bit more than 3 clock cycles. There are also cases where it might be lower than 1. This means that multiple of these instructions can be executed at the same time. So execution time then of a block would then be just adding up all the costs of each instruction. But this doesn't require, this is not as accurate as it can be because, so no, my bad. Yeah, this can be done very quickly, and we don't have to execute the code, we don't have to compile it, but it is not as accurate as it could be because the typical compiler optimizations cannot be applied to this code. Although we have the measurements here that are averaging the numbers, it does not contain the information, okay, is this loop here even executed or not? So this would be a very simple loop for iterations, and the compiler might decide, okay, it's not even required to execute this. We have more.
Just Oliver, sorry, I've got 2 questions that have come up. Is this a good time to ask you the questions now, or is it? Am I interrupting you too much? I've already done it. Yeah, sorry, I've been waiting patiently a little bit. There was one question basically quite a little while ago asking, it's a pity you couldn't show the MATLAB model before going into the performance estimation. I suppose there's a reason for that, right?
Well, I wanted to just give a short teaser or outlook what the results might look like, and I will go into the example after showing a bit of theory what we are doing.
And that explains
then I will show at least the C code. Unfortunately, I don't have the MATLAB model here, but I can show the C code and a bit of the structure, how the program looks like. So that some background there is shown.
Yeah, that also explains what you meant by outlook, basically looking at the results, and then later we'll go through the process in more detail. There's another question, and you may answer that later as well. The question is how much configuration and how many steps, or manual configuration and how many steps are there needed between the MATLAB model and the report. Difficult to say how many steps, but I think the idea eventually is, of course, that this runs in an automated flow. So you basically check in your models and you then get the estimation without any manual steps in between. Is that realistic?
Our current approach here is to rely on the code generation of either TargetLink or embedded coder. So we are targeting a workflow where such kind of tool is already integrated, and then no additional configuration is required. So if we have the C code with the normal information, so normal information here means with some information about how to map the C code back to the original model, we can do the analysis. So no further configuration required if these tools are or if the code generation is already part of the flow.
Yeah, but I mean, obviously, if you know your models and your functions and so on, then you can configure things according to your knowledge. Yeah, so both are possible. Yeah, can be automated and can be adapted to your specific needs. Okay, sorry for interrupting. It's always difficult to find the right time.
So yeah, I was here showing how to make it more precise. So instead of just looking at the C code, the next step is looking at an intermediate representation here of a compiler. What we are using here is the LLVM compiler. And here some generic compiler optimizations are already applied. So whether a loop is executed or not, this is already optimized. So some code transformations are applied, and then we can basically use the same costs per as from the C code and have a more accurate optimization, more accurate estimation based on compiler optimizations. The disadvantage of this is that it doesn't take into account special optimizations for the actual target platform. So this is just as a generic front end to get some additional compiler optimizations into it. And now the most accurate estimation is looking really at assembler code. The idea is we use the C code. We compile the C code using the actual target compiler, and then we map the information that then we perform our performance results, performance estimation, and then we map back the results to the actual C code, and from there to the actual model. This has the advantage that all compiler optimizations are applied and that the actual target platform is targeted. So this is much more accurate because, yeah, we have here each operation that the target platform or that the processor can execute. We know the costs of each instruction. So this is coming from the data sheet, so no measurement involved here. And we have a more accurate model that even models the pipeline steps. So here integer, load, store units of the target platform. And with that, we can get much more accurate numbers. But the disadvantage of this is, of course, we need a bit more time, compilation, calculation. You have some inaccuracy with the tracing back. So this means that we can calculate the numbers, but the propagating it back to a single instruction or single line in C code is not possible. But looking at the model, it will be accounted for the correct subsystem or block where the actual instruction occurs. And one small disadvantage is also that it needs to be compilable. So you need to have here really C code with everything that is required so that you would be able to compile and run the code. Now, how do we do the mapping from C code to Simulink? We look at the generated C code. There are some additional comments above the actual C code. So here we can see our table lookup. It has a path. So this is the actual path from the Simulink model. Some additional information can be like this combined comments here. This means that this expression here with here multiplications is combining a gain module with a product and a TargetLink output. So three blocks in one line of C code. There are some additional information. So when there are loops, there might be some auxiliary variables or variables that only belong to a subsystem. So these look a bit more complex, but can also map back to original blocks. And what we now need to do for performance estimation, we need to be able to calculate the self-time. So what is the self-time? Self-time is the time it takes to execute a single function or a block of the model. And this means only that block and not everything that is part of it. So for example, here we have a switch block. This switch block is basically an if, okay, with a condition, and it has a true and a false path. And inside of the true and false path, we can see here bus import, local variable, storing something. So everything that is really happening inside of the C logic here is not actual timing of the switch. So here we need to subtract execution times from other blocks. So there is some logic involved to actually get the timing of the self-time of a block. And we need that self-time to be able to model the timing of each of the overall system. Now, this was all theoretic background. Let's look at an example program. So we have here a quadcopter example. The idea is we have a program that is modeled partially in MATLAB and partially in C code. This means we have here a system that is calling different tasks. each task has a specific functionality, so engine controller, some observers, just to control the overall system. And each of these tasks are implemented inside of a Simulink model, and then the C code is generated for it. So we have a look at this. We have an altitude observer. This is C code generated from the Simulink model using TargetLink. And what we can find here are different comments. We have different instructions. So this is the C code that is coming out of TargetLink without any additional configuration. What we have here is a C code just to bring everything together. And for our estimation, we need one entry point. An entry point is typically one function. And this could be either one of these tasks, but here, just to be able to show a bit more, we have an additional function that basically calls out all of these tasks. This would typically be done by an operating system, and you could analyze then one task for the tasks individually. But to showcase everything all at once, we have created this run all tasks. Now, if we perform the performance estimation here inside our tool, we will get this kind of representation. This is a hierarchical representation of the performance estimation. And hierarchical means we have the x-axis, the width is basically the time it takes to execute a block, and the y-axis is the whole structure of the program. Now, we started with Simulink blocks. Simulink blocks would be function calls, and here we can see it on this level. So this would be function of the task 1, so one controller. Here is the task 2 engine controller, task 3, and here we can really find all of the 6 tasks. These would be the original blocks from the Simulink model. Now, if we go higher, you can see, okay, there is another function that implements it. Then typically you will find something like a step block. So if you start with the Simulink block, these step blocks are generated to model the logic of each individual block. And we can see here, going higher, this tabular axis, this would be an array axis, looking for searching through an array to find a specific value. Now, if we look at the colors, we can directly see, oh, there is something orange. So this is a warning color here inside of our tool. And this means we have here now a do-while loop. If we look at the actual source code here, this is a do while a variable is smaller than another variable, or at least a subtraction of another variable. So this is something that cannot directly be analyzed statically. So we don't know the values, or we try. So in this case, we don't know the value of this and this variable. So we don't know how often this loop is executed. We have logic for constant propagation. So if there is some logic inside the source code to set these to specific numbers, we are able to calculate the number of iterations. But if we are not able to do it, then we highlight it as orange. We can see it's now set to 10 iterations by default. But this is something that we can change. So if you know your block, you might know, okay, this is accessing an array, and you know that the way the data is organized, maybe you need 20 iterations on average. So you can specify it to 20 and then just run it again. And what happens now is it's not orange anymore. It's now blue, has a 20, and we can see that the runtime ratio here became bigger. I think before it was 17 point something microseconds. So now it takes more time. So you can specify these numbers however you like. So you can, if you know your logic, you can set here better numbers than our default value. The default value 10 here is just there to show that there is a loop. So this always means, okay, we have here a loop, and we can see that this body is executed 10 times. If we would use a default value of 1, it would be much shorter. So here, this is clearly there to highlight that there is a loop. And even if you don't have numbers, this you can use the estimation also with the default values, at least if you use the numbers in relation to each other. So if you make now some changes to the original model, you regenerate the code, run the performance estimation, and then you can see, now it's 10% faster, 10% slower, whatever the change is. This change is consistent even if you don't have the all the numbers for the loops. So you can directly see whether it is an improvement with the runtime or it takes more time with the new implementation. But if you want to use this number really as an upper limit, and you need to ensure that a certain runtime is not reached, then you need to specify all of these loops. Besides the loops, there are also if blocks. So these ifs here, if a value inside of the table, so a certain condition is met, then something else is happening. Here we typically estimate it with 50% true, 50% false. So this is the same case here. You can specify how often this condition is true. A typical use case is also an enable signal. So if you have a Simulink block with an enable input, then you typically know whether it is true or false. So it's either 0 or 100% enabled, and you can set this as well. Now, everything that you set here is stored inside of a file. So you don't need to always use the graphic user interface. So if you do this configuration once, you have this JSON file, you can store the information inside of this file and reuse it later on. And don't specify it anymore. Or even if you want to run it without a graphic user interface, you can do that as well. Now, I specified this. From here, we can also see what kind of values are used. So we have here, for example, this assembly view. So this means we have here for each task, or for each block of the original model, what is the corresponding assembly code. We can also see what kind of information is used for the actual performance estimation here. And then we can see, this observer here has these kinds of instructions, most of it on the load store pipeline, some latency here, and here some integer pipeline processing, and might also use some floating point operations. All these numbers are also specified in target platforms that are using here configuration files. So here there is a JSON file just for the costs of the instructions in the C code, but also for the whole assembly calculation. So here we have the whole table, and this can be modified, or if you have a different target platform, you can also write this yourself to create your own custom device that maybe has some different timing, has additional operations, or just has a different configuration. So here our hardware is also modeled with an XML file. So here you can define what are the processing cores available. Do we have some kind of accelerators? What is clock frequency? All that is configurable, and you can define your custom platforms. Same is also true for functions. So if you're using libraries, you typically have some kind of functions where you don't have the C code, so memcopy, memset, or even some print functions. So you can specify either a single value here. So this would be just, okay, this function takes this amount of time, but it's also possible to model this in a bit more complex fashion. So here the idea is that this depends on, so memcopy, for example, depends on the actual size of the argument. So you can specify here some calculation so that you can model a black box functionality that is not actually part of your source code, but is run or is called from the code. You can also see here for printf, for example, it is currently set to 0. Printf is something that typically should not be part of the actual program that is executed on the target platform. Now, if we generate the performance reports for this example now, we have, for one, this report that I already showed you. So this is all now based on the static source code analysis of the program. And we have all the information here about the subsystems and of the blocks of the model. And the way we analyze it, we can provide average number. So this would be the typical use case, but we also have minimum and maximum cases. Minimum and maximum here, so at least for the maximum part, this is important. So this is not actually something like what you would call the worst case execution time, but only the maximum runtime by the analysis of the input source code. So if we look at, for example, an if block, we have one true and one false path. One of them is longer, so the maximum path is taking the longer one. Same is for loop iterations. If the number of loop iterations have some kind of slack, so minimum and maximum have a difference, or so there might be some conditions where we don't have, where we have a smaller number of iterations, then the maximum would be the maximum number depending on the actual input data. Yeah, with this kind of report, you directly can see where time is spent, but we also have here a list of unknowns. So what kind of information is unknown for the actual block? We can see here first, so we have always these 4 numbers. The first one would be functions. We can see there are, at least for the top ones, no unknown functions. We can see, yeah, some have 4 unknown loops. So these would be the do while loops. And we can also see the ifs. So here, for example, 22 if blocks where there is no, nothing additional assigned to it. So we don't know. So we have to assume 50% true and false. And if we want to analyze this a bit more, we have an additional report. This report here relies on the actual C code. So we find all the functions, we find the timing, but it also has an additional section about unknowns. So here we can directly see these are the do while loops. We can see this if block here is also something that is unknown. We can see this one is executed 40 times. And we can see also the impact on the performance estimation. So just because we don't know the result of this one, this has an impact of 0.001 milliseconds, and this is sorted. So the ones at the bottom here are not that important anymore. So just to improve or to get really reliable results here, it's important to have at least the numbers for the loops and for the top if blocks. If you specify this, you can reach an accuracy level that is around 90 to 95% compared to measurement on hardware. So there are always some differences because the actual hardware has caches, or there is some timing issue, or there is some timing that cannot be analyzed statically, like waiting for a bus or for data from a memory. So there is some slack here, but for a platform like the Oryx that is very reliable, very deterministic, you can reach up to 95% of the same numbers as measurement on hardware. Now, how can all of this be used? So I showed you how it can be used inside of the graphical user interface. This is really if you want to analyze a specific model, look into the details. But a more typical integration would be using it in a continuous integration workflow. Here, the idea is, okay, you have here your CI flow, and typically you have some kind of build step and then running automated tests, but you can insert just an additional analysis pass, and this would perform the performance estimation and can generate the HTML reports that I showed you. So these could be available then directly from the CI server. You can just go to a web browser, get the results back, or you can also run the whole analysis, have a project file, and open this project file directly at the piece at the development side. So you can look at the actual timing and analyze where most of the time is spent. And if you run this inside of a CI flow, this is very useful to track changes over time. So every time something is changed inside of the source code, then a new report is generated and you can build the difference to previous reports. Yeah, this would be the graphical representation. So this is stored inside of the as part of the CI run and can be opened with its own version of the tool. And the HTML reports, yeah, directly accessible through the web browser. Now, the benefits of such an integration are, yeah, that you can benefit very early in the development process from this performance estimation. So you can make more informed design decisions. Then you get continuous monitoring if you do it all throughout the whole project. So yeah, any changes that affect the performance, either very positive or negative, can directly be looked up and compared to, yeah, why is it correct with this with this latest code changes or model changes, or was there some kind of error? The detailed information that you get will help you to understand the timing behavior of models. So where is most time spent inside of the model? And this will also help during the development of the functionality or preventing any timing issues later on, or at least knowing where these timing errors might occur. So which are the high runners or the critical parts of the program. And yeah, using it will also ensure that your code is ready for the actual hardware tests. Okay, that was it with the overall presentation and demonstration.
Yes. Okay. Thank you, Oliver. I mean, just to make it clear to everybody, I had written it in the chat. If you have questions, let's just put them in the chat, and we'll try and answer them quickly now. Not many questions. There is one. Is the tool able to advise blocks which could be replaced in the model because the timing is better? So now we're going from analysis to optimization. This is the kind of outlook that I thought we would get into at some stage. But Oliver, your answer maybe first.
So yeah, currently we are not able to make any suggestions. So we can only show you where most of the time is spent. And we had the experience that a function developer has at least has a timing behavior in his mind, and that looking at these reports really showed some surprises. So most of the time is spent in this table access, or most of the time is spent here, although the actual functionality should be somewhere else. So this really was helpful to so that the function developer was able to fix the issue. Currently, we're not able to make any suggestions because it's not always simple to see what the functionality should be. So there are some cases where it's clear that, for example, these table accesses are not implemented in a very efficient way. There we can give out warnings that there might be a different option, but maybe the option was selected because of accuracy reasons or memory requirements. So there we cannot make guaranteed suggestions that are always better. So the code generation will always try to make the best out of it already, but depending on the actual blocks and configurations, it might not have the options to improve it any further.
But this is obviously an area where there will be some development in the future, where we basically are looking into the question: how can we, based on our analysis, how can we point the developer to, let's say, routes of improvements? Yeah. I do not see any other questions. Hopefully, I haven't overlooked anybody. If not, then just send me another quick message in the chat. I think this is pretty much everything answered then. And then I think we'll just have to thank you for your attendance. Thank you, yeah. And, wish you a good rest of the Tuesday. And if there are some other questions, you know where to find us, yeah? Okay, thank you very much then. Thank you, Oliver.
Thank you for your attendance. Bye.
Bye for now.